Welcome to Lab SC1, Transverse Standing Waves on a String. The objective of this lab is to study propagation of transverse waves in a stretched string. You'll be using an electrically driven speaker, a power amplifier for the speaker, a bridge, and pulley and table clamp assembly. Begin by attaching the DIN9 pin and the power cable to the amplifier. Then connect the power amplifier to the speaker with the cables. Also, set up the table clamp and pulley assembly. Add weights as described in the manual. The setup consists of an electrically driven speaker which sets up a standing wave in a string stretched between the speaker driver system and a pulley. In physics, a standing wave, also known as a stationary wave, is a wave that remains in a constant position. It can arise in a stationary medium as a result of interference between two waves traveling in opposite directions. This is an example of a standing wave in stationary medium. The red dots represent wave nodes. This wave is in fourth mode. Notice that the points colored in red are always stationary. Similarly, these are the examples of standing waves which are oscillating in different modes. To begin the experiment, launch Data Studio, create an experiment, and select Power Amplifier as your instrument. The signal generator window will then pop up. You can use this window to set up the amplitude and the frequency of the speaker input. For the first part, set the frequency to 60 Hz. The frequency of the wave is equal to 1 by lambda times under root f over mu, where big F is the tension in the string, mu is the weight per unit length of the string, and lambda is the wavelength. Place a sheet of paper provided on the table. This will make it easier to see the vibration of the string. Measure accurately the length of the string between the bridge and the pin of the speaker using the 2-meter ruler. At 60 Hz, calculate the necessary string tension to produce a standing wave in the third or fourth mode. Adjust the string tension to find the tension which results in the largest amplitude. At 60 Hz, the largest amplitude in the first mode will look something like this. Keep adjusting the weight until you get the largest amplitude. For part 2, choose 6 masses between 100 gram and 1 kilogram of weight and record the values. Then determine the resonance frequency of the string under these different tensions and record your results. When you plot your results, you can see how the frequency varies with M. Also, now plot a graph of frequency versus the root of M. Note that you can use the slope of this curve to get the mass per unit length of the wire. In the end, you should be able to answer which of the two graphs can be fitted with a straight line, and which one with a parabola, and why.